Okay, guys, welcome. Today we're going to talk about RSA encryption. Now, RSA encryption, or reversed Shamir and Adelson encryption, is the first public key encryption that was successful on a large scale. All right, so just a little bit of background. Public key encryption is speculated to be invented by Clifford Cox of MI5, which is the British Secret Service Agency. But due to the secret nature of cryptography, the early history is not, of course, entirely known, right? So we're going to need the following theorem before we discuss this. Now, we're going to suppose that a, n, x, and y are integers, and we're going to suppose that a and n are both integers that are greater than 1, and that the GCD of those two numbers is 1. So a and n are, of course, relatively prime. So if x is congruent to y mod phi of n, remember phi of n or phi of n is a number of primes less than n that are relatively prime to n, then it follows that a to the x is congruent to a to the y mod n. Okay, and now let's prove this. So by the assumption, we know that x is equal to a multiple of phi n times some integer k plus y, right? That's what this means right here. That means that when you divide when you divide x by phi of n, you get a remainder of y, right? That's what that's saying, right? Well, then by using some exponent rules, we know that since x and y plus phi of n times k are the same, then by using our exponent rules, we can separate them. And then we have a times y times a to the phi n to the k, right? But a to the phi of n is congruent to 1 mod n. And this is by, I believe it's down here, right? This is by Euler's theorem, which is a generalization of Fermat's little theorem. All right, so that proves the result there. Okay, so now let's talk about how RSA encryption works. Okay, so we're going to suppose that Bob wants to post public information that will allow Alice, whom he has never met, to communicate securely with him. Okay, so what's going to happen is that Bob generates two large random prime numbers, each of which is thousands of digits long, or even more than that, right? And we're going to call these two random primes P and Q, and we're going to define n to be their product. Now, Bob also generates a number e that is relatively prime to phi of n. And of course, that means that e and p minus 1 times q minus 1 have a GCD of 1, or they're relatively prime, right? Now, again, why is this true here? Well, because we know that phi of n is phi of p and q. And if p and q are relatively prime, and of course they have to be because they are primes themselves, this is phi of p times phi of q. And phi of a prime number is just the prime minus 1. So it's p minus 1 times q minus 1. Okay, now Bob computes his decryption exponent, which we call d, which is the solution to this number e times d congruent to 1 mod phi of n. Now, of course, this is fairly simple to calculate, knowing the things that we know. And of course, since we're still new to this idea of cryptography and modular arithmetic, it might take us a little bit to get the hang of it, but it's fairly simple to calculate, right? We could do it, even for large numbers, because of this modular thing. Now, Bob makes public the numbers n and e, and this is what we refer to as the RSA public key, right? So anybody could view this information if they want. Now, Alice wants to send Bob a message which is coded as an integer n, right? Where this number m is between 0 and the number n that we mentioned before. Now, Alice computes m to the e mod n and is going to send it to Bob, right? Now, if somebody wants to intercept this message, it would be hard to do this because m to the e is going to be a large number, right? And of course, mod n is a huge number as well, because n is made up of those two extremely large primes. Now, since Bob has the value d, he's going to find m to the e all to the d power mod n, right? Which gives him m, since e times d is 1 mod 5n, right? And then, of course, by this theorem stated at the beginning, m to the ed is congruent to m to the first mod n, right? So now Eve, who's an enemy of Bob, would like to know, of course, the decryption exponent d so that she can intercept the message, right? So to find this, Eve would need to solve e times d is congruent to 1 mod 5n for d. The problem for Eve is that she does not know how to factor n, right? And since n is made up of two extremely large prime numbers, it's very hard to factor n. Right? And then since it's extremely hard to factor n, it would be hard to find phi of n, which of course is good for Bob and Alice because they want to protect their message. Okay. Now, one thing that we did gloss over was the fact that in order to apply the theorem, we needed the GCD of m and n to be 1. Okay. Now, Alice's choice of m does not force this to be true, but it would only fail if the prime that Bob chose divides m, or the other prime q also divides m. And the fact that this happens is very unlikely, right? So it's somewhat probabilistic in this sense. Now, of course, just like with all cryptography, this is somewhat subject to variability, right? Because if it's sort of stuck in the same format for too long, then then you can sort of decode messages a little bit easier. Right, so to summarize what RSA encryption is we generate two large primes, and they should be large enough that factoring p times q by hand is essentially impossible. All right, now what we'll need to do is we'll also need to perform arithmetic with numbers whose size is on the order of p and q, right? So those two large primes. Then the next thing we do is we generate a number e that is relatively prime to phi of n. Right, then we solve the equation e times d congruent to 1 mod phi of n for d. And then finally, Alice would need to compute m to the e mod n, and Bob would need to compute m to the e to the d mod n. And of course, we would like to do all of these things quickly so that interceptors don't have the time to decode the messages or decode the algorithm. Right, so we'll talk a little bit more about this sort of concept in the next video. I hope you enjoyed, and I'll see you next time.